Hi and welcome to Specialist Mathematics, Unit 1, Topic 1, Video 12. In this video we're going to look at Venn diagrams and the inclusion-exclusion principle. And of course there is our success criteria and learning goals. Definitely worth having a quick read of this and making sure you're happy, and then reading it again at the end, which might mean rewinding the video a bit. So of course you'll need to recall some elements of this from your work in math methods. Firstly, set notation. If A is a set, then it contains a series of unordered objects such as, and here's an example. Now, in this example, I've given A the value, the odd numbers below 10, B, the set primes below 10, and C is a set of even primes below 10. Now, you can see that C is going to be a subset of B purely based on the definition there, and you can also see that 2 is the only element of C, and it's contained within B. So there's a few important words there. First of all, subset, which is this notation. C is fully contained within B. And element. So there's a set contains a series of elements. And these elements, as I've started at the top here, may be ordered or unordered. It doesn't really matter. But when it comes to numbers, it's probably best to order them. So we can also use this symbol to represent the null set. And therefore, the null set contains nothing. It's still a set. It's a set with nothing. It's not nothing. It's a set that contains nothing. So it's treated a little bit like 0 is in arithmetic, as in if you add 0, it changes nothing. And we can also use these sort of magnitude lines here. That denotes the number of elements in A in this case. So if we had those two vertical lines, we're asking how many elements are contained within the set A. Now, hopefully you've seen some Venn diagrams before. We're going to talk about A and B and talk about them with regards to Venn. Now, you can see within A and B that we've got 1, 2, 3 common elements. And then A has two elements that are not in B, and B has an element that's not in A, and then there's some other elements below 10 that aren't included in either. So it's a nice little situation. But firstly, let's use colours to denote some other language. We have the intersection. Now, the intersection is the connection between two sets. So A and B has an intersection, and it includes the numbers 3, 5, and 7. Numbers that are odd and prime, below 10. And then there's the union. The union is when you combine the two sets together, irrespective of whether it's in both or just in one. So the union is the numbers that are odd or prime. So this language here is really important. And is associated with intersection, and or is associated with union. Now, the odd or primes are 1, 2, 3, 5, 7, and 9. So let's have a look at a quick example. And this is to do with sets A and B. From the sets defined A and B, calculate A and not B. So it's worth saying, first of all, that A dash, or maybe A bar occasionally, but usually A dash, is not A. So that's what it means. So in this case, A is the elements 1, 3, 5, 7, 9, the odds below 10. So A dash is the evens below 10. And in this case, I'm assuming 0 is not included, as it's not a counting number. And so we're talking 2, 4, 6, 8. And because it's below but not equal to 10, we won't include 10 either. So from the sets defined as A and B above, calculate A union B. So union is everything in both. But it's A union not B, so this will be equal to the set that contains all of the elements in A, which are the odds 1, 3, 5, 7, and 9, and all the elements in not B. So B is the prime numbers, not B is the not prime numbers, so I have to include in here 2 is a prime, but 4, 6, and 8. And then I could order that if I want to. So that's basically every number but 2. And then the elements not A and not B. So this is the intersection. So what elements are in not A and also in not B? And not A is the even numbers. Not B is the not prime numbers. So this will be 4, 6, and 8. Not A and not B. And then A and B and not B. Well, this is a bit of a trick question because B and not B, what elements exist in B and also exist in not B? This is the null set, or a set that contains nothing, not 0, so it contains nothing. And then A or B or not B, another bit of a trick question. So if it is an element in B or not B, every element is in B or not B. So based on my earlier definitions, this is 1, 2, 3, 4, 5, 6, 7, 8, 9. And we decided not to include 0 or 10. So there's our solution to example 1. Now, additionally, there's some other things that are important here, including the inclusion-exclusion principle. So firstly, the probability of A occurring is the number of outcomes where A is favourable divided by the total number of possible outcomes. So the probability A in the previous question, or in the previous example, A was the odds. There were 5 odds and 4 evens and 9 in total, so it was 5 on 9. And also don't forget that the sum of all probabilities must equal 1. Now, the inclusion-exclusion principle, it's called that because you have that inclusion within the Venn diagram here, or whether we exclude certain values that are out here, for example. But the principle that's on your formula sheet is that A union B is equal to the elements in A union B is equal to the elements in A plus the elements in B minus the elements in A intersection B. So that means this is the number of elements in A here in purple. And so I might just grab my purple. This is purple. And this is blue. Blue is the elements in B. But if you add purple and blue together, which is what we're doing in this formula here and here, well, we've double counted that intersection bit, the middle. So we have to subtract from that the orange here because we've double counted that intersection. And it leaves us, of course, with the green. So we can say that the green, which is the union, is equal to the purple plus the blue minus the orange. It's a really helpful principle. Note here, with a little bit of algebra, we can also rearrange this to say that A and B, which is intersect, is equal to the elements in A plus the number of elements in B minus the number of elements in A or B. So we can flip that around as well if needed. Similarly, and not on your formula sheet, you get the same idea with a 3-part diagram. You've got A, B, and C, but it's a bit more complex, and it's something maybe you could play with. But you'll notice here that we add all of our number of elements in A, B, C separately. We subtract the pairings, but then we add back on the triple. And this pattern actually holds. If you go to 4 or 5, we do add all the singles, subtract all the pairings, add the triples, subtract the quadruples, etc. So we've got a final example now. 100 people who play either golf or tennis were surveyed. And of the 100 people, 68 play golf and 47 play tennis. How many play both? So play both is the union. So let's define golf as G and tennis as T, which means that play both is the number of people in the set G and T. And the number of people in the set G and T is going to be the number of people in the set G plus the number of people in the set T minus the number of people in the set G or T. And in this case, that's going to be 68 people play golf, 47 people play tennis, minus 100 people in total that play golf or tennis. Notice the or there. And 68 plus 47 is 115 minus 100, and so the answer is 15. There are 15 people that play golf and tennis to make this possible. And if I draw this out quickly as a Venn diagram, keeping in mind there's no one in this question that plays neither. The question starts with 100 people play golf or tennis, so this is 100 people, and we're stating that that's 15. Now this whole circle is 47, this is the tennis circle, which means that this part is 32. This whole circle is 68, this is the golf circle, which means this part is 53, and 53 plus 15 plus 32 equals 100, as expected. So there we have the inclusion-exclusion principle, and this is the last video of our series on combinatorics. So go back, have a look, start practicing questions that relate to any area of combinatorics, and make sure that you can do them irrespective of what's being asked. All the best.